Right. So in the previous class, we were discussing the two transistor model of SCR. Okay. See, very simple. If you see the top three, okay, if you see the top three regions, you have P and P. So that is equivalent to a PNP transistor. Now, if you see the bottom three regions, you have NPN. So that is equivalent to an NPN transistor. Okay. Already the top three regions I have drawn. Okay, right, in the previous class. And what is this top? Okay, I will take the same color. What is this top? This one is anode. Okay, this top is anode. Okay, same anode. Next, what is this bottom P region? It is the gate terminal. Okay, same. Now let me draw the bottom NPN transistor. Okay, let me draw the bottom NPN transistor. I will draw here. Okay, here I will draw the bottom NPN transistor. Okay, so the bottom NPN transistor. Right? So top three regions are PNP. Top three regions are PNP. So PNP transistor. Bottom three regions are NPN. So NPN transistor. But okay, what happens here is, see, this N region is common, correct? Okay, right? So if you see top PNP transistor and if you see bottom NPN transistor, what is common in those two transistors? This N and P is common, right? So this N and P is common, this N and P. So if we overlap, okay, so this is like PNP transistor, this is like, okay, NPN transistor. If we overlap such that the middle P and N regions overlap, then the complete SCR is formed. So the trick is the middle two regions should overlap. Okay. So how will we represent that? We will represent that by giving a connection between this N region and this N region. Then this P region is connected to this P region. Okay, right? PNP transistor, NPN transistor, if you merge the two NP, okay, middle N and middle P regions, then you get an SCR. Okay, so that is what is two transistor model of SCR, right? And as we know, what is the bottom terminal? The bottom terminal is the cathode. We are representing by K. Okay, right? Now all we have to do is we have to name this transistor. Okay, we will call this transistor T1. We will call this transistor T2. Okay, then identify, okay, and replace the PNP region with PNP transistor, NPN region with NPN transistor. Okay, right? So that is what we have to do next. So first of all, let us name the regions. Let us name this, okay, T1, right? So emitter, I will call this emitter E1, okay. Then base, okay. Then collector. Because first transistor, I will put one here. Emitter, base, collector, EB1, okay, E1, B1, C1. Next, likewise, let us name here, okay? Let us name like this, okay? Emitter, let us name it as E2, okay? Then B2 and then C2. E1, B1, C1, E2, B2, C2. Why we took like that? Because in transistor, emitter is heavily doped, okay? So in SCR, if you see, okay, if you see the structure of SCR, first region is heavily doped. So this first P region, you can take it as emitter. Next, last N region is also heavily doped. That you can take as emitter. So top region you can take as emitter. Bottom region also you can take as emitter. Okay. That is why we are taking, okay, that is why we are taking like this. Emitter base collector, emitter base collector. Okay, clear? And because T1, we are putting subscript 1, emitter 1, base 1, collector. Transistor 2, T2, so E2, B2, C2. Now all we have to do is replace this structure of the transistor with the symbol of the transistor. Okay, that is what we will do next. So first we have to draw a PNP transistor. Okay, so first it's from top you have anode, okay, followed by PNP transistor, but this time emitter, right? I hope you remember this is the, okay, this is the symbol of the PNP transistor. Just a minute. Okay, so this is the symbol of the PNP transistor. Okay, right? Arrow into the base, right? From emitter into the base arrow. So this is the symbol of the PNP transistor. Next, okay, so this is emitter, okay, E1, right? Emitter E1, and this is base B1, collector C1, right? So I will call this current as I E1, okay. Then I will let us call this current as, let us call this current as, okay, right? Let us call this particular current as IB1, okay. Let us call that current as, okay, I will call it as IB, right? Because the, okay, first current through the, okay, current through the base of first transistor, so we will call it as IB1. Okay, next, what do we have here? We have to draw one more transistor. The base of, okay, the base of first transistor is connected to collector of second transistor, right? So this point we have to connect to the collector of second transistor. Okay, okay. So that point we have to connect to the collector of second transistor. So this one is the second transistor. So this is collector. So obviously this one will be the emitter. Okay, right? And then you have to join. Okay, see here. Collector of first transistor is connected to base of second transistor. Okay, collector of first transistor connected to base of second transistor, right? Okay, so this is the structure. Then let us call this current as, okay, let us call this current as I. This is second transistor. So collector of second transistor, let us call it as IC2. Okay, right? Next, collector current of first transistor, let us call it as IC1. Okay, I will call it as IC1, right? Okay, next, what is this terminal? This is the cathode K. Okay, and additionally, to the collector of first transistor, what is connected? The gate terminal is connected. Okay, so what we are doing here, we are replacing the structures of the two transistors with the symbol of the two transistors. Okay, right? Next, what we will do here is we will consider, okay, two cases again here, when gate is open, when gate is closed. Okay, so case one, first case. Okay, case one, gate. When gate is open, what happens? Okay, right, we will consider now. So when gate is open, first of all, what can we call this particular current as? We can call this as I. Okay, we can call this as IB2. Okay, base current of second transistor, right? We can call it as IB. So what happens here? Okay, when gate is open means IG is 0, right? Okay, gate is open. Okay, let me represent IG also here. Let me represent IG. Okay, right? So what do you mean by gate open? Gate open means, okay, implies IG is 0. Okay, so IG is 0 means, okay, IG is 0 means, okay, what is the situation? IB2 will be 0. Okay, right? There is no supply, there is no gate current, so IB2 will be 0. Correct? So when IB2 is 0, transistor T2, okay, this one, this is transistor T2, this is transistor T1. Okay, T2 will be off, no base current, so T2 is off. T2 is off means IC2 will ideally be 0. Practically leakage current will flow, which is IC0. Okay, but because you have the second transistor, we will call it as IC02. Okay, we will call it as IC02, right? So next, we will consider, okay, when this IC02 is 0. See here, if you see this path, IB1 is flowing like this, same path IC2 is flowing. Okay, so IB1 is equal to IC2, right? So what we have here, we already have IC2 is IC0. The same thing will be your, okay, the same thing will be your IB1. IB1 is same as IC2 because path is same. Correct? Now what happens when, see here, IB2 is negligible, leakage current. Okay, so because of that, what happens here is, okay, because of that, I will write here. Because of that, what happens is, okay, because of this situation, what happens is, okay, transistor T1 will be off. Transistor T1 is off. Okay. T1 is off means, what do you mean by T1 is off? Okay. It means this IC1 is also, okay, ideally 0, but practically leakage current will flow. So IC1 is now leakage current. Okay. So we will call it as IC naught. Leakage current is not IC naught. Okay. And because it is first transistor, we will take it as IC not 1. So in simple words, what happens when gate is open? Gate is open, IG is 0. IG is 0 means IB2 is 0. Okay. IB2 is 0 means T1 is off. Sorry, sir. IB2 is 0 means T2 is off. Okay. Let me write here. What is the meaning of IB2 0? T2 is off. Okay. T2 is off means IC2 is only leakage current. What is the leakage current we call? We call it IC naught. And because it is second transistor, we are putting IC naught 2. So because T2 is off, IC2 is IC naught 2. Okay. And IC2 is equals to IB1. So IB1 is also IC naught 2. Right. So IB1, base current of this transistor is, okay, base current of this transistor is also very small, negligible leakage. Base current is small or 0 means transistor is off. So T1 will be off. Okay, right? T1 is off means IC1 is also leakage current, which is IC naught 1. Okay. So the total anode current will be simply leakage currents of this one and this one. So the total anode current, okay, will be simply, the total anode current will be simply equal to IC naught 1 plus IC naught 2. Okay. Because only leakage currents are flowing. Both transistors are off. T2 is off, T1 is off. Only leakage currents are flowing. So if you see the net current here is divided, one in this path, another in this path. The current here is IC naught 1. The current here is IC naught 2. So the total anode current, which is IE1 actually, okay, is nothing but IC naught 1 plus IC naught 2. So this is what happens under the case of gate open. Okay. Next we will consider what happens if, okay, next case we will consider what happens if gate is closed or gate current is no longer 0. Right. Next, that is what we will consider. Right. So that one, let me write here. That one, okay, I will write here. So next case, right? Next, we will consider what happens when the okay, we will discuss that here. So next, when, okay, let me choose different color. Okay. First case, Ij was 0. Now, what happens when Ig is increased? Okay, when this Ig is increased, then Ib2 will increase. Okay, right? So I will put up arrow for increase, down arrow for decrease. Okay, so when Ig is increased, okay, then what is increased? The Ib2 is increased, right? Okay. When Ib2 increases, Ic2 increases, transistor is moving towards saturation region. Okay, we have seen that many times. So what happens? What happens because of that? Okay, what happens because of that is when Ib2 increases, then okay, implies Ic2 increases, right? Ic2 increases. Now, when Ic2 increases, okay, when Ic2 increases, that Ic2 is nothing but the base current of the transistor T1. We have seen Ic2 is nothing but Ib1. Okay, so it simply means Ib1 is increasing. Okay, Ib1 is increasing, right? So when Ib1 is increasing, then the transistor T1 will start conducting. Okay, transistor T1 is conducting means when this happens, okay, Ib1 is increasing. So when that happens, what happens? This IC1 will start increasing. IC1 will start increasing. Okay, so when IC1 increases, if you see this diagram, when IC1 increases, okay, current start to flow like this. It will flow into the base. Okay, so as a result, this will further increase the Ib2. Okay, that will further increase the Ib2. Clear? Okay, so suppose if you increase gate current, what happens when you increase gate current? This path, current in this path is increasing, so obviously Ib2 is increasing. So when Ib2 increases, okay, you supply base current to transistor, collector current increases, Ic is equals to beta Ib, you know that relation. Okay, so when excuse me, when Ib2 increases, Ic2 increases. Ic2 is nothing but the base current of first transistor. So when Ic2 increases, Ib1, okay, is increasing. Base current of transistor is increasing, means collector current also increases. So IC1 increases. So when IC1 increases, see this IC1, when it increases, the current has to flow through this path. So Ib2 will increase. The cycle will keep on repeating, and in short time, okay, right, both the transistors will turn on. In very short time, both transistors will turn on. Till what time this cycle will repeat? The cycle will repeat until both the transistors turn on. Okay. Then what happens is, okay, the characteristics will jump from this point to this point. Clear? Okay. Characteristics will jump from this point to this particular point. So that is what happens. Okay. Inside the SCR, and the two transistor model explains that very clearly. Okay. Next topic we will discuss is tunnel diode. So tunnel diode is somewhat difficult. Okay. So I recommend that all of you put at most concentration for that. Okay. So in what way tunnel diode is different to ordinary PN junction diode? Means it is very heavily doped. Okay, PN junction diode, right? It is also PN junction diode. Tunnel diode is also a PN junction diode. Okay, right? The only difference is it is heavily doped PN junction diode. Okay. So anode, cathode, okay, same anode, cathode, P region, N region, very heavily doped. Okay. Tunnel diode is simply a PN junction diode which is very heavily doped on both sides, P region and N region. Okay. We have discussed several times that when doping is high, width of the depletion region is thin. Doping is high, width of the depletion region is thin. When width of the depletion region is thin, then charge carriers can easily penetrate through the depletion region. Okay. Hence, the name of the device tunnel diode. Tunnel means tunneling. You know tunneling. Okay. The meaning of tunneling is penetrate. Right. Okay. So electrons can easily tunnel through. Okay. The charge carriers can easily tunnel through the depletion region. Why? Heavily doped. Okay. Heavily doped means thin. Heavily doped means thin depletion region. Okay. Thin depletion region means electrons can easily penetrate or tunnel through the depletion region. Hence, the name of the device is tunnel diode. Okay. To understand this, we have to consider energy band diagram. Okay. I believe energy band diagrams are somewhat new to you. So put more concentration, and suppose if you don't understand, watch this video again. Okay. Still, if you have doubts, don't hesitate to ask me. Okay. But basically, it is very simple. See, there is something called as Fermi level. You have to remember. What is that Fermi level? Ante, till there you have electrons. Okay. Definition is, okay, it is the highest level occupied by electrons at 0 Kelvin. Okay. In simple words, till Fermi level, you have electrons. Okay. At Fermi level and below Fermi level, you have the electrons. So first, we will draw Fermi level. Okay. We will draw the Fermi level. Okay. I will call it as EF. EF, Fermi level EF. Okay, right? Then this is P side. Okay, this is N side. Correct. So here I will do one thing. I will draw this somewhat at the top. Okay, I will draw here. This is P side. Okay, this is N side. You know very well that in the P region you have holes. Where the holes reside means they reside in the valence band. Okay, right? So there is valence band below. Okay, there is valence band below, right? Fermi level is the highest energy level that electrons occupy. Okay, right? Means till Fermi level you have the electrons. Okay. So what do you have there is, let me draw two more lines. Okay. So till here you have electrons. Okay, let me shade the electrons I will shade. Okay, till here you have electrons, right, in the p side. Then you have vacancies, which are holes, and holes will be in the valence band. Okay, right? So from here to here, all this will be the valence band. So this one you can represent it as, okay, this one we can represent it as the valence band. In fact, it is the highest level of valence band. Valence band is this and below that. Okay, right? Then above the valence band, you have conduction band. See, actually, what do you have? Say, if you take an atom, right? Inside the atom, the electrons have energy levels. Only in that particular energy level, you know, planets, they orbit only in particular orbit, right? And they follow that orbit. Same case, inside the atom, the electrons, they have energy level. Okay, they only are available in that energy level, right? And the outermost energy level is the valence band, right? And once the electron comes out of the atom, it is ready for conduction. Then you say that the electron is in the conduction band. How does an electron come out of the atom, or how the electron comes out of the valence band? You give energy. You can give heat energy, light energy. Okay, right? Taking that energy, the electrons from the valence band, they come out and they go into the conduction band. Okay, so we are representing something called as the conduction band, right? So what do you mean? Okay, this gap is known as Eg from here to here. Okay, this gap is known as energy gap Eg. Okay, what is the meaning of that? Means, suppose if you have charge carriers in valence band, you give an energy Eg, then they will jump into conduction band. Means, okay, it is in the valence band. Okay, electron, suppose electron is in the valence band, means it is not, okay, free to conduct, right? Now when you give an energy Eg, it comes out of the atom, it goes to conduction band, means free to conduct. That diagrammatically we are representing like this. That concept, okay, diagrammatically we are representing, so that we understand what is happening inside the solid. Okay, fine. So this is the situation in the p side. What about excuse, what about the n side, right? If you see n side, Fermi level is where the electrons reside. Okay, highest level of electrons. And we know n side, free electrons are there. So already you have electrons in the conduction band. Okay, so the lowest level of conduction band will be, okay, below the Fermi level. The lowest level of the conduction band. This is Fermi level EF. Okay, same Fermi level, constant. And below that Fermi level, you will have the conduction band EC. Okay, and obviously below EC, you will have the valence band. Okay, obviously below the EC, you will have the valence band EV. Okay, always below EC, you will have EV, and the difference between these two is nothing but the energy gap. Okay, is nothing but the energy gap Eg. Okay, right, same energy gap Eg. So the complete band diagram for tunnel diode, okay, the complete band diagram for tunnel diode will be, okay, p region, n region we have drawn. Next what we have to do is join this conduction to conduction. valence to valence. Okay, the energy band diagram of the tunnel diode will be complete. Let me see if I can draw with free hands. Okay, fine. That's a straight line, right? Take it as a straight line, and then this point we will join here. Okay, so this is the energy band diagram of a tunnel diode, right? And I told you till Fermi level you have the free electrons, right? So there are free electrons here till the Fermi level, correct? Then energy gap, I told you as atoms they have orbitals. Electrons also have orbitals, okay, or energy levels, right? In that energy gap, there are no electrons, no free, okay, no electrons. So in this shaded region, you have the electrons, right? Okay. Because energy band diagram is new to you, study this thoroughly. Again, I will explain in the next class. Okay, I'll explain this again in the next class. Study thoroughly. I'll try to explain on board and okay, I will record, right? Instead of showing the